So in this lecture I want to explore some of the properties of denumerable sets and try to understand how they interact with things like subsets, supersets, intersections, unions and Cartesian products. To understand how does the property of being denumerable, is that preserved under any of these things? So let's just take a look. So denumerable sets. So one of the things that's very interesting about denumerable sets, which is going to help us prove all of these results, is that a set is denumerable means that we can list out its elements. Now that list will be infinite, but we can actually construct a nice infinite list of those elements. And to see this, remember that since a set is denumerable, we have some function that takes us from n to b that is a bijection. And those bijective properties tell us nice things. So in particular, we can write out b as the image of 1, the image of 2, the image of 3, the image of 4, and so forth. So this, whatever f maps 1 to is the first thing in our list. Whatever f maps 2 to is the second thing in our list, and so forth. And so this gives us a list, b1, b2, b3, b4, b5, so forth, where the nth thing in the list is the image of the natural number n under the function f. Now, because f is a bijection, this gives us two nice properties of this list. First of all, since f is injective, it means that different inputs always give us different outputs. So if we have two positions on the list, k and n, well, bk is fk, so that's the kth thing on the list, and fn is bn, so the nth thing on the list. Because k and n are different and f is injective, we know that their images are different. And so the kth thing on the list is always different from the nth thing on the list. So this means that the list does not repeat. Further, and this one's a little bit more subtle, since f is surjective, given any element of b, so for all elements of b, you can always find a natural number n, so that that element is the image of n. Now this means that any given element b of b will be the image of some finite natural number n. So this means any given element of b always appears at a finite position in the list, because this n here from the natural numbers is always a natural number, so it's always some finite natural number, okay, because no natural number is infinite. So this means any given element of the list that you choose, any given element of b that you choose, you can always find it at a finite position. Now that finite position might be way down the list, but it always has to appear at a finite place in the list. And we'll see some examples of when that becomes important in just a moment. Now notice, this is saying that if a set is denumerable, then we can list out its elements. But we can actually turn this around. If we can list out the elements nicely in a similar way, then this is giving us a bijection, and so telling us the set is denumerable. So say we can write out the elements of b in a nice list, and we'll explain what nice means in a moment. So we'll write b as b1, b2, b3, b4, and so forth. So we're writing out all the elements of b in a list like this. Then we can use that list to construct a bijection from n to b. So of course we need to understand what nice means and understand that this will actually be a bijection. So what do we mean by nice in this context? Well, first of all, let's define this function g, which takes us from the natural numbers to b, by saying the image of k is just the kth thing in the list. So the image of 4 is b4, so g of 4 will be this thing, okay? So we're using the list to define what the image of any given natural number is by just looking up the list to see, hey, what's in position n in the list? That's the image of n. Now, this list will be nice when it tells us that g is both injective and surjective. So it will be nice when it does not repeat. So this list not repeating means that different points in the list are always different, and that's enough to tell me that g is injective, because it's saying, hey, different inputs will always give me different outputs, making g injective. The list will also be nice provided any given element of b, so any given element of b can always be found at a finite position in the list. So for every element of b, there is always some position in the list so that you can find y as the nth thing in the list, and that of course gives me g of n. And that makes g surjective. And so if we can construct such a nice list, namely things don't repeat, and any given element of b appears at some finite place in the list, then this constructs a bijection from n to b, making b denumerable. Okay, so this gives us a way of producing a bijection which doesn't rely on us having a nice formula, it just relies on us being able to construct a nice list. And this is much easier, and it gives us the bijection implicitly rather than explicitly. This will help us prove a bunch of results. So let's see it in action. So first of all, let's prove that the set of all integers is also denumerable. So this is telling me that z is actually the same size as n. Okay? So the natural numbers are the same size as all integers. And this is weird because, of course, the integers feels like it should be twice as big because it contains everything positive, everything negative, and 0. So it feels like it should be twice as big as the natural numbers. But this is an example of one of the weird things that infinite sets do that finite sets do not do. And it's also an example of why we really need all that machinery of functions to help us navigate this weirdness. Okay, so let's see how we make this work. So we're going to do it by making a nice list. So we need to list out all the integers, so everything in z, so that the list does not repeat, so that we're defining an injection, and so that any given integer appears at some finite position in the list, so that that function is also surjective, to make sure it's a bijection. Now, making sure the list doesn't repeat, that's easy, we just don't repeat ourselves. But the second one is a bit harder. The second condition, making it surjective, is a little bit more difficult. So if we list out z in perhaps a very naive way, we might say, hey, well, z is just ... -2, 0, -1, 1, 0, 1, 2, and so forth. So that, we have everything going off to minus infinity that way, everything going off to plus infinity going the other way. And this is, of course, a list, a bi-infinite list, you'd call it, where that's fine, except everything's appearing, nothing's repeating, but I, for example, have no idea what position on the list that is, other than to say, well, it's at position infinity. And that's not good enough, because I need to know what natural number n gives me f of n equals 0 in order for this thing to be surjective. Okay, so that's not good enough. Now, we could do something else. We could say, well, right, I'll do all the positive things first, and then everything not positive second. So I'll do all the positive numbers, and then at some point I switch over to 0, -1, -2, -3. But then we're still faced with the same problem. What position on the list is this at? So that is, what natural number n gives me f of n equals 0? What's the position of this in the list? And it doesn't, in both of these cases, I don't know that 0 appears at some finite position in this list. And indeed, by the way I've constructed this, it doesn't appear at some finite position. So the right way to do it, amongst many other right ways to do it, but this is a very natural way to do it, is to just start off with 0, 1, -1, 2, -2, 3, -3, 4, and so forth. So just start with 0 and alternate positive, negative, positive, negative, positive, negative, positive, negative. Because now if I look at this list, you can see that everything appears on this list. It doesn't repeat itself. And any number will appear at position, well, roughly 2 times its absolute value. So what have we got here? 1, 2, 3, 4, 5, 6. So for example, 3 appears at position 6. Okay. So this list will not repeat, and any given integer will appear at some finite place in the list. We can make this a bit more rigorous on the next slide. So let's prove that z and n have the same size, that there's a bijection between them, and we do that by listing out the elements correctly. So we're going to list out the elements of z as we did on the previous slide, namely 0, 1, -1, 2, -2, 3, -3, and so forth. Or equivalently, we're constructing this mapping, this bijection, from the natural numbers to the integers by 1 maps to 0, 2 maps to 1, 3 to -1, 4 to 2, 5 to -2, and so forth. And you can see here that all we're doing here is listing out these things by their position on the list. So the 6th position gives me 3, so 6th position gives me 3. Okay, so if we list out all the elements of z as here, or here, then we see that any positive integer appears at position 2z, and any non-negative integer, non-positive integer appears at position 1 -2z. And you can check that these are right. And if you really wanted, you could make this into a single function of f of z to try to work out exactly how to write it down as some concise formula, but this is good enough. We don't need to do that. We just need to describe how to construct the list. And notice very explicitly we see that the list does not repeat itself, and any given integer z appears at some finite position in the list. So this list, because it doesn't repeat, and any given thing appears at some finite position, gives you, at least implicitly, a bijection between n and z, and so we have that these things are the same size. This is one of the first sort of weirdnesses we see with infinite sets. All right. Now, this next result is going to show us that there's no smaller infinity. There's no weird infinity that sits between denumerable sets and finite sets. So the way that this works is if we take two sets A and B with A as a subset of B, then if B is a denumerable set, then any subset has to be either finite or denumerable, that is, countable. There's no other possibility. It's either a finite set or a denumerable set. And the proof of this is a little bit technical in places, so I'm just going to give a sketch of the proof. Well, first of all, if A is finite, then there's not much to do, because if it's finite, it's countable. So we really only consider the case where A is an infinite subset of this denumerable set B. Well, if A is infinite, it suffices to construct a bijection from N to A, okay, to show that it's denumerable and so countable. Now, since B is denumerable, by assumption here, we can list out its elements, B1, B2, B3, B4, and so forth, just as given to us by the implied bijection, because B is denumerable. Now, since A is a subset of B, we can just delete the things in this list that aren't in A. And so you can see here, just as an example, so example only, I've deleted B2, B3, B4, and so forth. Okay, no, I haven't deleted, I've deleted B2, B3, and B5, because I'm going to say, hey, those things aren't in A. So I'm just going to cross them out from the list. And I'm going to get a new list for A, which is just the things that I didn't delete, namely B1, B4, B6, B9, B13, and so forth. Again, example only here. This isn't all sets A. This is just the example that I'm giving here. But notice, this new list, because I didn't add anything to it, I just deleted things, well, since the original list was nice, it didn't repeat itself, the new list for A doesn't repeat itself. Further, given that A is a subset of B, any given A in A appeared at some finite position in this original list B, and so when I delete things, it's still going to appear at some finite position in the list of things for A, probably just a bit earlier. And so this list of things in A, generated by taking the list of things in B and then chopping things out, doesn't repeat itself, and any given element of A appears at some finite position, so it's nice, and so this gives us implicitly a bijection between A and N, meaning that A is denumerable and so countable, and so giving us the result. And this shows that any subset of a denumerable set is either finite or itself denumerable. There's no other infinity in between. So we can put this to work pretty quickly. Let's take any natural number k, then we can form these sets of kz and kn. This is just all multiples of k and more multiples of k, either all integers that are multiples of k or all natural numbers that are multiples of k. Well, both of these sets are denumerable no matter which k we pick in the set of natural numbers. Now, we could prove this by constructing explicit bijections between kz and z, or kn and n, but we can also just use the previous theorem, because both of these things are subsets of z, and we know that z is denumerable. So by that previous result, we know that these sets are either finite or themselves denumerable, okay, by that previous theorem. Well, because they aren't finite, you can see that pretty clearly, it follows they must be denumerable. So these sets here, where we basically knock out everything except every kth element, those are also denumerable. So deleting a whole bunch of elements doesn't stop things from being countable. Well, what about unions and intersections? Well, if we take two countable sets A and B, then their intersection and unions must also be countable. Well, okay, well, if A and B are finite, then everything's going to be finite, so that's not so interesting. If A is a subset of B, well, if A, no, let me repeat that. A intersection B is always going to be a subset of A, so if A is countable, then all its subsets are countable, and so that intersection is going to be countable. That follows by the previous theorem. On the other hand, well, if A and B are countable, and, well, maybe infinite, not finite, well, notice that we must have that B minus A is countable because it's a subset of B. So what I'm going to use here, one reason I'm looking at this is I'm going to write A union B as A union B minus A, because I want to avoid repetition. And so the elements in this union must either be in A or in B, but not A. So I'm just being careful here. By writing things this way, using this little fact, I can list out elements of A that are not in B and elements in B that are not in A, so that I don't repeat anything. So A and B are countable. B minus A is countable because it's a subset of B, and B is countable by the previous theorem. And so we can list out the elements of A as A1, A2, A3, and so forth. I can list out the elements of B minus A as B1, B2, B3, and so forth, okay, because these are both countable sets. I can list out their elements. And then I can just combine the sets by alternating. So this is reminiscent of what we did with Z. Now we went negative thing, positive thing, negative thing, positive thing, I'm just going to do the same sort of thing. I'm going to take the fact that A union B is A union B minus A, and I'm going to put an element of A, element of B, element of A, element of B, element of A, element of B. And this list, by construction, won't repeat anything. And because the original list had that nice property that any given element appeared at some finite time, any given element of this union appears at some finite position in the list. So this way of listing things out is still nice. Now, of course, if one of these sets is finite, say if A is finite, well, then I can just list all the things in A first and then all the things in B, and it'll still have that nice property that all the things in A appear in some finite position and all the things in B appear at some finite position. And by setting things up carefully, by doing this sort of thing, I can make sure I don't have any repeats in this list. Okay. So unions and intersections don't let us escape from being denumerable. Well, what about Cartesian products? Well, Cartesian products also are not enough to get us away from denumerable or countable sets. So if A and B are countable, the product is always countable. Now, the finite case is kind of obvious, I hope, but let's think about the infinite case. So if A and B are both infinite, namely A is denumerable, B is denumerable, then I can list out their elements, A1, A2, A3, B1, B2, B3, and so forth. So we can list out the infinite list. We make those infinite nice lists of the elements. And I can use that to construct a table of all the ordered pairs. So this is now a big two-dimensional thing going off to infinity that way and infinity that way. But it contains all of those ordered pairs that come from this Cartesian product of A times B. So A1, B1, A2, B1, A3, B1, and so forth. Now I can construct a list of all the ordered pairs by traversing this table in careful ways. So for example, I could start here and then read off things doing this sort of traversal like that. You know, I could make some pattern like that where I just zigzag my way through the table, reading off everything in the table in some careful manner. Now, the wrong way to do it, just to show you the wrong way to do it, would be to say, hey, I'm going to sweep through the first row and then the second row and then the third row. Now, while that list would have everything, I wouldn't actually know when I would get to this thing here. What position on the list would this element be at? Because I would have to go all the way off to infinity on the first row before I got to here. So I'd never get to this element in some finite time. So it's important that I traverse it in some careful way. And perhaps the most standard way to do this is by looking through diagonals. So we sweep through a diagonal like this, and then like this, and then like this, and so forth. So sweeping through diagonals like that, you can see that I'll reach every element in the table exactly once, so it's no repeats, but also that any given element must appear on some finite numbered diagonal and so must appear in some finite time in my list. Okay, so that's one way to do this. And so we can make that into a bit more of a formal proof. So if the sets A and B are denumerable, we construct that table of all the ordered pairs like this, and then we sweep through successive diagonals like this in order to see all the elements in the list. So by sweeping through the diagonals, we list out all the elements of A times B. So for example, we can write A times B as A1, B1, A2, B1, A1, B2, A3, B1, A2, B2, 1, 3, and so forth to get this big infinite list. And this list will not repeat. And any given ordered pair, so for example, A, N, B, K, will appear on, say, the n plus k minus 1th diagonal, and so appear in some finite time. And so this means that that list is nice, in the sense that we described earlier, making this Cartesian product also denumerable. Okay, so the Cartesian product isn't enough for us to escape. Now, this also gives us this really weird result, namely that the set of all rational numbers is denumerable. Now, this is really weird because the set of all rationals is dense. This is very different. Namely, between any two rational numbers, you can always find another rational number. And this is very different from how the integers behave. The integers feel much looser because, well, there's a finite gap between any integers. But the set of rationals is very, very different because you can always look more and more and narrow, focus down and down and down, zoom in and zoom in, zoom in, and you always find more rationals. So this is a very weird result. So to see how this works, well, let me get my tablet working here. Note that any element of Q can be written uniquely as A divided by B, with A in Z and B in N, and this fraction reduced as much as possible. So the GCD between A and B is 1. So any common factors have been removed. So any rational number can be written uniquely like this, where the numerator is in Z and the denominator in n, and the GCD of those things is 1. Now, because of this, because we have this unique way of writing things down, we can rewrite the rationals as some set of ordered pairs, where the first thing comes from z, and the second thing comes from n, and so that a and b have no common factors, namely the GCD is 1. And we have this bijection given by, or a bijection between q and this set p given by, hey, if I take this fraction written in lowest terms, namely a divided by b, then turn that into just the ordered pair, a comma b. Okay, so this gives us a bijection between q and p. Now, p, just by construction, is a subset of z times n. So z times n, well, that's denumerable, so the Cartesian product is denumerable, and so any infinite subset of that denumerable set must also be denumerable. So we know that p is denumerable. But since p and q are in bijection with each other, we know that q is denumerable as well. So this is a very, very weird result that the rationals are actually just the same size as the integers. This is a very weird thing that infinite sets do. And I think that's where I'm going to stop.